Welcome to Conversion Factors 101, and by popular demand I'm going to do a simplified tutorial on how to use conversion factors. So let's start out with some metric prefixes that we have discussed in class and that you should know. And kilo, which is abbreviated big K, means 10 to the third or 1,000 major units. Centi, little c, is 10 to the minus second units, or 1/100th of a major unit, such as 1/100th of a meter. Milli, little m, is 10 to the minus third, or 1/1000th of a major unit. Micro has a funny capital or funny cursive U-shaped symbol, is 10 to the minus sixth of any major metric unit, or a millionth of a unit. Nano, small n, is 10 to the minus ninth, or a billionth of a unit. And pico is 10 to the minus 12th, or a trillionth of a unit. So let's make some conversion factors using this information here. We'll start out with nano. Okay, and by the way, nanometers, billionth of a meter, is really the scale at which we talk about the sizes of atoms and molecules. So conversion factors always look like fractions. And for nanometers, we could say there are 10 to the ninth nanometers in 1 meter. So what this means is that the quantities in the numerator and in the denominator really are equivalent in value. It's just that their units are different, and therefore the numbers are going to be different. But 1 meter in length is equal to 10 to the ninth, or a billion nanometers in length. I can also write this conversion factor as 1 meter in 10 to the ninth nanometers. So we have two different conversion factors here. Now, why do we need two? Well, it really depends on the problem that we have in front of us and what we need to solve for. So really the rule is that the unit here that's in the numerator, this is the unit we are converting to. And the unit here in the denominator is the unit that we're canceling out. And so if we keep that in mind when we solve our problems or work through our problems, it will be easy to determine which conversion factor we want to use. So let's say that I have 1.75 times 10 to the minus second meters. And I want to know how many nanometers that is. Well, then the conversion factor that I need to use is going to be this guy, because nanometers is in the numerator. That's the unit we're converting to. So 10 to the ninth nanometers in 1 meter. My problem's already set up. And you'll notice that meters and meters cancel out, and we're left with nanometers, which is what we want in our answer here. Okay, so when we work the problem, this becomes 1.75 times 10 to the minus second times 10 to the ninth. And when we multiply exponents, what do? We add them. So minus 2 plus 9 is 7. So we end up with 1.75 times 10 to the 7th nanometers as our final answer. Let's say that I have 3.5 3.759 times 10 to the 23rd nanometers. And this time I want to convert into meters. Now I'm going to use this conversion factor up here. Why? Because meters is the unit I want to convert to. Nanometers is the unit I want to cancel out. So I have 1 meter in 10 to the 9th nanometers. And I can double check that, and I can see that nanometers is here, they cancel out. I have meters here in the numerator. That's the unit I'm looking for in my answer. So my problem becomes 3.759 times 10 to the 23rd times 1 over 10 to the 9th. Mathematically, that's equal to 3.759 times 10 to the 23rd divided by 10 to the 9th. And when you divide exponents, you subtract them. So 23 minus 9 is 14. So I end up with 3.759 times 10 to the 14th, and my units are meters. So the big thing to remember is, in our conversion factors, the units we convert to go in the numerator. The units where we want to cancel out go in the denominator. Okay? So we're back to conversion factors 101. Now this is part 2. So let's pick a couple other guys over here. Let's make some new conversion factors. Let's see, I'm going to work with, let's see, milli and kilo. So for kilo, I can write, if we're using meters as our common unit, all right, in 1 meter, that would be 10 to the minus 3rd kilometers. Or easier, I could say that in 1 kilometer, there's 10 to the 3rd meters, or 10 to the 3rd meters in 1 kilometer. Okay, these two guys are really ones that you use more often than you would this guy. Okay, so I'm going to cross him out for right now. And for milli, there are 1,000 millimeters in 1 meter. And I could also write in 1 meter, there's 1,000 millimeters. So let's say that I have 5.678 times 10 to the 7th millimeters. And I want to know how many kilometers I have. So I'm jumping right from millimeters to kilometers. When I look at my conversion factors here, this is millimeters to meters. Okay, and this is meters to kilometers. So the easiest way, the most straightforward way of doing this is by using 2 conversion factors. So the first thing I'll do is I'm going to convert from millimeters to meters. So I'm going to use this conversion factor. Remember, I want to convert to meters, so meters goes in the top. 1 meter in 1,000 millimeters. And then I can go from meters to kilometers. Okay, so here's the conversion factor I need. I want kilometers, so kilometers goes in my numerator, and there's 10 to the 3rd meters in a kilometer. So I've set up my problem, and I can see how my units cancel out. Meters and meters cancel out. Millimeters and millimeters cancel out. I'm left with kilometers. That's what I want in my answer. Okay, so my problem becomes 5.678 times 10 to the 7th, all right, times 1 over 1,000, which is really 1 over 10 to the 3rd, times 1 over 10 to the third again. Okay? And when we simplify, it's 5.678 times 10 to the 7th divided by 10 to the 6th. Remember, when we multiply by 1 over something, it's the same as dividing. And when we multiply exponents, we add them. Okay, so now we have a division problem here. Again, we subtract exponents. So I end up with 5.678 times 10 to the first kilometers. So in this case, I have a conversion factor problem that involves 2 conversion factors. Now, some of you may be able to do it in just one step and say, well, hey, I know that there's 10 to the third, over here, meters in a kilometer, and 10 to the third millimeters in a kilometer, and I know 10 to the third of 10 to the third is 10 to the 6th, so I'll just multiply this number here by 10 to the 6th and I get my answer, which is essentially what we did. But what I did here is lengthen it out, put it into 2 conversion factors, and really the reason I wanted to do that, the ultimate reason, is that later on in the year, when we get to stoichiometry, we're going to be solving a lot of problems where we have not 1 conversion factor, but 2, 3, even 4 or more conversion factors. So you need to get used to making sure you can put them in the logical sequence so that their units cancel out and give you the units that you want in your answer. In conversion factors part 3 of 101, what we're going to do now is do some conversion factors using density. So let's look at some common densities. Okay, gold has a density of 19.3 grams per centimeter cubed. Aluminum has a density of 2.7 grams per centimeter cubed. Ice has a density of, I think, 0.917 grams per centimeter cubed. Gasoline has a density of about 0.66 grams per centimeter cubed. So we can use any of these densities as a conversion factor, believe it or not. So let's say we take ice. I'm going to choose ice. I can write the density of ice as 2 conversion factors. I can write it as 0.917 grams in 1 centimeter cubed, or in 1 centimeter cubed, I have 0.917 grams. As in any conversion factor, the quantities in the numerator and denominator are equivalent, but they have different units and therefore different numbers. But really, if I had a centimeter cubed of ice, it would have a mass of 0.917 grams. And that's what both of these conversion factors are saying. So I can use that to solve any density problem. So let's say that I have a big ice sculpture. Okay, what are we going to have? What's our ice sculpture going to be? What do we usually make ice sculptures of? Okay, don't laugh at my drawing, but some kind of bird with wings. All right, and tail, maybe some feet. Okay, there's my ice sculpture. Okay, and let's say my ice sculpture has a volume of 200,000 centimeters cubed. Okay, 200,000 centimeters cubed. And by the way, how many liters would that be? That would be 2 liters, because there's 1,000 cubic centimeters in a liter. I want to know what's the mass of the ice sculpture. Okay, so I want to know the mass. I'm starting with the volume. 200,000 centimeters cubed. Let me change my color here. Go to blue. So I have 200,000 centimeters cubed. I want to know the mass. So I can use one of these conversion factors. Which one am I going to use? Remember that the units we want to convert to is going to be in the denominator. So I'm going to choose that guy. I want grams in my numerator because that's what I'm converting to. The units I'm converting to go in the numerator. Hopefully I didn't say denominator before. Could have. It's getting late this evening. I'm tired. So 0.917 grams in 1 centimeter cubed. And when we look at our units, we can see that centimeters cubed and centimeters cubed are going to cancel out. So our problem becomes 200,000 times 0.917. So that's the math that we have to do. And when I punch that into my calculator, I end up with 183,400. My units would be centimeters cubed. Now I have a little bit of an issue here. I have a significant figures issue. Oh no, not that. Yes, that. How many significant figures are in 200,000? There's no decimals here, so all my zeros are placeholders. I only have 1 sig fig. So what am I going to do here? Okay, oops, this should be grams. Told you I was getting tired. We're doing mass here. I would need to round this up to 1 sig fig. So we're rounding it up to this place right here, my 100,000s place. Well, guess what? It ends up being 200,000 grams. That is rounded to 1 sig fig. Okay, if I had put in like a decimal here and here, that would have given me not 1 sig fig, but 1, 2, 3, 4, 5, 6, 7, 8 sig figs. And then I could have included this whole number plus some decimal places and had a more precise answer because I had started with a more precise measurement. But that, unfortunately, wasn't the case. Let's say that I have 552 grams of ice are knocked off this ice sculpture. Okay, some kid comes along and kicks off the wing. Oh no! Okay. We have this little kid over here. He decided that he was going to give this old ice sculpture a big old kick and knock off the wing. Okay, what a doofus. But anyway, we want to know what volume was kicked off. So what is the conversion we're going to use? We're going to go and use this guy because we want to know centimeters cubed. So centimeters cubed goes in the numerator. So 1 centimeter cubed in 0.917 grams. So our problem becomes 552 divided by 0.917. So I got to plug that into my trusty calculator. And I get 601.96. What are my units going to be? Remember that grams and grams cancel and left with centimeters cubed. So my units are centimeters cubed. How many sig figs do I need? Well, here I have 3 sig figs. So my answer has 3 sig figs. How do I round this to 3 sig figs? I need these 3 number places. I look at the next number. It's greater than 5, so that means this guy, the 1, needs to round up. So 601.96 rounds up to 602 centimeters cubed. Okay. So using densities as conversion factors makes density problems really pretty easy. There is, of course, an alternative way of doing that, and that is remembering that density is mass divided by volume, and of course you do need to know that. And if we want to solve for mass, okay, we'd multiply each side here by volume, and so we'd get mass equals volume times density. Okay? if we look at density equals mass divided by volume, and I want to solve for volume, okay, what I'd be doing this time is I'd end up with volume equals mass divided by density. All right. So if you're good at manipulating the equation algebraically and just, plugging and chugging, putting the numerical values in here, you can do it that way. It's essentially the same thing. They are the same things mathematically. I think it's easier to do density as a conversion factor, and then you can just look at the units that need to cancel out. But if you want to algebraically manipulate the equation and do it that way, be my guest, okay? There's two ways of doing it. So hopefully I didn't make too much of a mess here and help you understand this. It's getting near to my bedtime. But again, this is part 3 of conversion factors, which is awesome because we can use densities as conversion factors to solve any kind of density problem. Happy studying for chapter 3.